Hello and welcome to video 4.2 Elastic Collisions. This is a continuation of momentum and momentum conservation. With elastic collisions, one of the most important aspects about them, is that momentum and kinetic energy are conserved. We already know that collisions can involve a wide variety of outcomes, and we typically classify collisions based on what is conserved in them. So elastic collisions conserve both momentum and kinetic energy, whereas inelastic collisions don't. And remember, when we have things being conserved, what that means is that the total amount of each thing before a process starts has to be equal to it at the end. So if we're having momentum being conserved and we have class elastic collisions, then we can assume that M1V1 initial plus M2V2 initial is equal to M1V1 final plus M2V2 final. If kinetic energy is conserved, then we can write a similar equation as we've done before. 1/2 M1V1 initial squared plus 1/2 M2V2 initial squared is equal to 1/2 M1V1 final squared plus 1/2 M2V2 final squared. With elastic collisions, both of these equations hold true, which means that both of these equations can be used to solve problems. One of the important things about elastic collisions is that for both of these to be true, this implies that there are no dissipative forces involved. In other words, no friction. You can see a great example of this in Newton's cradle, because if momentum and kinetic energy are conserved, then it's an elastic collision, and then Newton's cradles act the way that they act, which is oftentimes opposite of what we expect them to act like. So let's take a look at a Newton's cradle for a minute here. So here we have a Newton's cradle, and we can pull one of the balls out and we can give it some kinetic energy, and therefore we can also give it some momentum. And if they are both conserved, then the total amount on this side has to equal the total amount over here. Well, we have the mass of one ball on this side at some speed. Over here, for momentum to be conserved, we could have two balls come out at half of the speed. However, our kinetic energy would not be conserved at that point. So in order for this to occur and have as an elastic collision, then when we hit one has to go out on the other side. Now you can see that the three balls in the middle move a little bit because they're just on thin wires, but pretty much not at all. So the energy is being transferred from the first one to the second. The second one doesn't move as much, goes to the third, to the fourth, to the fifth, etc. Now let's see what happens when we take two. Again, it's an elastic collision, so for kinetic energy and momentum to be conserved, our total kinetic energy over here must equal our total kinetic energy over here. We have two masses over here at a particular speed. We cannot just have one mass come out over here at a greater speed, because kinetic energy would then not be conserved. So we go ahead and release two, and two go out the other side. Again, conserving both momentum and energy. And the third one still sort of sits there. If we make it a 3, if we pull 3 out, now what do you think will happen? We're still conserving energy and momentum. The third one has to continue moving back and forth in order for both of those things to be conserved. So this is an example of an elastic collision, or many elastic collisions, where both kinetic energy total energy and momentum are conserved. So if we get back to what we were saying before, that we could use these equations to solve a problem dealing with elastic collisions, let's see what one of those problems would look like. Oh, I guess we're going to look at some cases first. We're going to look at some things some situations that could occur and what would happen with both of these being conserved. In case one, if we have two balls colliding, let's assume that they're colliding head-on for the moment, then when they collide, if the second one is at rest initially, afterwards their velocities will have been exchanged. So the first one will stop moving and the second one will start moving at the speed that the first one had been going. We saw this in our last video when we used the PhET simulation. If we change it a bit so that the first mass is considerably larger than the second mass, and the first mass is moving at a speed of v1, when it hits the second mass is going to shoot out quite fast. In fact, it will typically shoot out at twice the original speed, and the large mass is hardly going to change its speed at all. Now, you might think that this would cause a total momentum not to be conserved, but that's why they say approximately equal to, because it is still being conserved. So the large mass loses a tiny bit of its speed, but we typically can't tell that by looking at it. Now in the third case, we have a super teeny tiny mass hit the larger mass instead, and the larger mass is sitting there at the speed of 0 to begin with. Afterwards, the super huge mass is still going to be approximately 0. Maybe it gained a tiny, teeny bit, but not much. And the tiny mass is going to go back the way it came with a speed equal to the same as the first speed. Sorry about the neighbor's dog there. But negative because it's in the negative direction. Now, what these little comments mean over here about not head-on, then theta is 90 degrees. If not head-on, then theta is less than 90. And if not head-on, then theta is greater than 90. What these are referring to is in the after the collision, if the balls are not hit exactly head-on, then in the first case they will end up going at 90 degrees to each other. In the second case, the angle between them will be less than 90 degrees, and in the third case, the angle between them will be greater than 90 degrees after they collide. All right, so now let's go ahead and take a look at a problem that is an elastic collision. We have a 2 kilogram mass moving at 12 meters per second. It collides head-on with a 6 kilogram mass at rest. If we know that the collision is elastic, what are the final velocities of the balls after colliding? Well, let's start by putting down what we know. We know that m1 is 2 kilograms. We know that v1 is 12 meters per second. m2 is 6 kilograms. V2, sorry, these are initials, is 0. The question is, what is V1 final and what is V2 final? Now, we can have two unknowns because we have two equations that we can use. We know that this is an elastic collision, so both energy and momentum are conserved. So I can start by writing the momentum conservation equation. m1 v1 naught plus m2 v2 naught equals m2 v2 final plus m1 v1 final. And it doesn't really matter the order in which you put them because it is just addition. We know that initially the second ball has a velocity of 0, so it has 0 momentum. We then have our kinetic energy equation, where 1/2 m1 v1 naught squared plus 0 is 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And again, the 0 here is referring to the second ball having no kinetic energy to begin with. So if I take a look at this, I can simplify this a little bit by saying, if I start with the energy equation here, I can simplify it by saying, well, the 1/2s go away, and then I have m1 v1 naught squared is equal to m1 v1 final squared plus m2 v2 final squared. Now I'm going to leave the energy equation for a moment, and I'm going to go back to my momentum equation, and I'm going to plug some numbers in and see what I end up with. m1 is 2, v1 naught is 12, m2 is 6, v2 final, we don't know, plus 2 times v1 final, which we also don't know. Well, I can cancel out a 2 from each of these, and I end up with v1 final is equal to 12 minus 3 v2 final. I'm going to take this information and I'm going to plug it right in to my kinetic energy equation that I have so far. So I have 2 times 12 squared is equal to 2 times 12 minus 3 v2 final squared plus 6 v2 final squared. So again, I can cancel out a 2 from each of these, and the left-hand side of my equation becomes 144. The right-hand side of my equation becomes 144 minus 72 v2 final plus 9 v2 final squared plus 3 v2 final squared. Because remember, you have to square this term here to come up with the quadratic. So we simplify this a bit. Our 144's go away, so we end up with 0 equals 12 v2 final squared minus 72 v2 final. Pull out a 12 and we get v2 final squared minus 6 v2 final is equal to 0. So I can get rid of my 12 there then, so then I end up with, and I'm also going to pull out a v2 final, so I get v2 final times v2 final minus 6 is equal to 0. So v2 final is equal to 0, or v2 final is equal to 6 meters per second. Well, since v2, since the 6 kilogram mass is originally at rest, chances are that v2 final is not going to be 0. It's not going to just sit there. It's not significantly bigger than the 2 kilogram mass. So we're going to say that v2 final being 0 is not a reasonable answer. So v2 final is 6 meters per second. We can take this and plug it back into this equation here. Find out that v1 final is 12 minus 3 times 6, which will give us 12 minus 18, so a negative 6 meters per second. So v1 final is a negative 6 meters per second. v2 final is a positive 6 meters per second. So after the collision, they are both going the same speed, but in opposite directions. Which makes sense because you now have something having quite a large mass going one direction, so you have to get rid of some of that momentum vectorially, shall we say, in the opposite direction. This goes through all of the basics of elastic collision problems that you could need to use to solve for final velocities. You might have to solve for an initial velocity or something like that. The key to solving elastic collision problems is to remember that both energy and momentum are conserved, and it doesn't really matter which one you start with in your solving, just as long as you make sure you remember to use both of them. Bye for now.